There we go. All right, so I actually am recording it this time. I had about 2 people ask, so. And welcome to the second lecture. I see a couple of people complained about the difficulty of the quiz. It was really tough, I know. I think they said that it took them 1.42 minutes was what it said. Yeah. Did anybody struggle more than that? Anybody do it? Well, yeah, because all you do is click a button pretty much. Low overhead. Let's see here. I am. There we go. The portable mouse, which in theory allows me to walk around. Okay. Let's see if it works. It does. All right, so as I mentioned on Tuesday, I'm trying to remember what day it is. I mean, I've been getting up around 5 in the morning and working until around 11 at night trying to get everything situated for the classes. Yeah, probably pretty much the schedule you guys are running too, right? So, I'm going to try every lecture to start from some sort of a concrete observable failure. My goal is to draw failures from the real world, not to make up shit. Not to say, oh, this is something that could go wrong, but to say, no, this is something that did go wrong. And ideally, I'm going to try and find examples of that where they happened within your lifetime. So today's example is from October 2025, which I think covers the lifetimes of at least some of the people in here. I mean, maybe you weren't alive on October 25th. You were passed out or something. It was a really good party day. I don't know, is UBC a party school? I have no idea. I mean, I went to probably one of the most non-party schools there ever was. So we're going to, and then we're going to talk about, so the idea is we want to start with a failure and then talk about what it is that we need to know in order to be able to deal with that failure. And one of the ways we deal with failure is we recover from it. Another way is that we try to build the system so they don't fail in the first place. Novel idea, right? And then we'll talk about how we build mechanisms to do that. Because in essence, that's what we're talking about. When you're looking at the second design project, which is in fact a Paxos implementation. Does anybody know what Paxos is? Excellent, excellent, good. Did anybody shake their head yes? It's an agreement protocol. An agreement is very easy, of course. You know that because anytime you ask your friends what they want to have for dinner, you all sit around and you just make suggestions that other people then veto. I don't really want to do that. I don't feel like that today. It's not much easier with computers. And computers are doing this typically at a distance. So they have a time component in them. But we have things like the TCP protocol, which is great, right? Because, of course, that guarantees reliability. But sometimes you don't want reliability. If your computer calls another computer and says, yo, what time is it? And the packet gets lost, do you want the time when it originally sent the packet, or do you want the time now? Yeah, you know, I actually learned this particular observation from one of UBC undergrads of long past. Because when I worked for him, which was a long time ago, he was a newly tenured professor at Stanford, but he graduated from UBC a long time ago. Must have been late 70s, actually. I'm trying to remember. Because he did his PhD at Waterloo. And then he came back here and he was a lecturer for a little while, and then he got a tenured track position at Stanford, and then I started working for him a month after he got tenure. And now he's retired and fabulously wealthy, one of the richest Canadians, and he didn't come from a wealthy family, he wasn't one of the richest Canadians. And a couple of you have already heard this story. The guy's name is David Cheriton. So that's kind of the UBC example of success. I mean, when they start talking about fundraising at departmental meetings, his name usually comes up because, of course, since he's worth like $10 billion, they're kind of like, maybe we could get a few million out of him. One of the interesting approaches anytime you start designing is to think about what would I need to do to prove my design is flawed. If you do proofs, formal proofs, what you actually try to do often is prove that you're wrong. Sometimes that leads to actual proofs that you're really wrong, in which case you have learned something, and sometimes it leads to an understanding of why it has to be right. You do the same thing in design. So we need to talk about what our failure models are. I mentioned one on Tuesday, which I can go back to now, which is the destruction of the Earth. You can't build a data center that's going to survive total annihilation of the Earth's surface. Well, maybe you could. So one of the important things you need to understand as you start to build reliable systems is, what am I trying to protect against? Anybody taking any security? In security, you start with a threat model. Think of this as a generalization of that idea. You're starting with a failure model. Anybody ever heard the term Byzantine? What does it refer to?
It's like a really complicated and kind of bureaucratic process is where I've heard it referred to the most.
Does anybody know the historical reference?
Byzantine Empire?
Mm-hmm. And what was the problem in the Byzantine Empire?
There were a few.
What was the problem that we typically identify it and use the word Byzantine to describe? Everybody lied. Lying was normalized. This is not any, there's no bearing at all whatsoever on what's going on in the current world, believe me. Everyone is absolutely truthful now, so we don't have to worry about that. In a Byzantine system, you have to assume everybody is lying. And the hard part about that is human society doesn't actually survive very long in an environment where everyone is lying. That's a particular failure model. But in fact, you can't tell when someone is broken versus someone is lying in distributed systems, in computer network models. I mean, is it sending me a bogus packet because it's trying to game me and break my system, or is it just simply broken itself and spewing out garbage? I mean, how many of you ever had a conversation with, I don't know, your favorite large language model, and it just said something you just looked at and said, that is completely, absolute bullshit? Is the failure in that case malicious, or is it just simply a bug? I mean, we use the term hallucination, which implies it's more of a bug than it is malicious. So in the network service model, what we have is a set of guarantees about what the services are provided by the network. When we talk about TCP, we give a guarantee that you're going to get everything in the order in which it was sent. UDP doesn't make that guarantee. It says, I'm going to get it to you, best effort. Sometimes things are going to get lost. They're not guaranteed to be in order. So you can solve your problems with either one of these, but you have to choose what the model is before you can design the solution. If you sit down in front of your keyboard and start trying to write a solution before you know the problem, I guarantee you're going to have a very difficult time making that happen. I mean, have you ever sat down and said, oh, I've got to do my homework, and you focus on building the answer without understanding the problem? It doesn't really work that well. You end up mashing your head into the keyboard. Is there anybody who has never experienced that? See, you have to ask questions correctly. If I'd asked everybody who had experience it to raise their hands, people would go, I'm not going to raise my hand. But no one who has experience it will raise their hand and lie, because that's actually extra effort. So the reliability is the policy, the mechanisms that you build on top of whatever the network is providing to you. If the network is providing unreliable datagram service, great. You know that, you know what to design. If the network is providing you with reliable ordered delivery, then you have a different set of constraints. If the network is local, you may be able to do things that you can't do across a real network. Anyone ever used this operating system called Linux? In Unix domain sockets, you can actually transfer a file descriptor over the socket. Say what? So program A opens the file and sends it to program B, and program B just uses the file descriptor that comes across. It doesn't have to open the file. It's a way of delegating access. Sometimes you use that when you're building isolation models, because you want something you trust to open the file, but then once it's verified that it's okay to share that with the other process, it can send that file descriptor, even if that process couldn't open the file directly. So today, what I want to do is get people to actually make sure that you're capable of, I think I saw a few submits, actually submitting to your Git repo that has been constructed for you on the GitHub server to make sure that you understand the principles behind signing your submissions. How many people have ever signed a submission before? I mean, there's a couple people, because there were a couple of repos I saw that had updates. A couple people. What is the purpose of signing something?
To provide proof that you looked at or interacted with it somehow.
Attestation. You are attesting to the fact that this artifact was created with your explicit or tacit permission. Now, of course, if you ever take cloud computing, we'll talk all about the ways that we get your tacit permission without you ever noticing. They're like little pop-up boxes that, like Uber likes to do that. Hey, sign up for Uber One! And you accidentally click on it one time and you can never get rid of it ever again, because the goal in cloud computing is to make it really easy to sign up for something and impossible to cancel it. We don't have to worry about that here. That's not the problem we're solving here. Here, what we're going to solve is distributed decision making. The reason that I've chosen to use this is because it provides something that's hard to forge, something hard to fake. Every time you submit code, there's a commit hook that runs that will actually update information and create a chain. In essence, it's creating a blockchain. You can spoof it if you want. It's not going to be particularly hard, but the idea is that if you wait till the last possible moment, you probably won't have the time to spoof it properly. And if you do figure out how to spoof it, like I said on Tuesday, hey, you learned something anyway. Today's failure is actually one that happened in October 2025, as I mentioned, and there's this service called Amazon Web Services. You probably never heard of Amazon. You probably have never used AWS, but it's this service provider that pretty much everything that runs in the cloud has some sort of a tie-in or dependency on AWS. The original problem was actually blamed on a DNS misconfiguration problem. DNS is, well, everybody's taking 317, so I can assume that everyone knows what the domain name service is. But what a lot of people don't realize is that, in fact, it turned into a broken system because of what's called a retry cascade, a retry storm. We send a message. We don't get the answer. We send the message again. and we don't get the answer. We send the message again, and we don't get the answer. And when too many people start to do that, what happens is we're all sending so many messages the responses can't get through. And this creates the situation where we just never stop. We just keep asking over and over again, please give this to me. And believe it or not, this is actually a problem in networking that's been around for a really long time, since way before probably anybody here was born. There's this thing called Ethernet. And in Ethernet, you can end up with broadcast storms. You can end up with reflection problems. You can end up with... does anybody know how Ethernet originally worked? I mean, we use star topologies now, which change the dynamics of it. But in an Ethernet network, what you actually had was a physical piece of cable. I know, at Stanford, we had it hanging in the gutters up there, and every 3 meters on the physical piece of cable, they would have a mark. And the reason they had a mark every 3 meters was because those were the points of reflection. Because standing waves can interfere with each other, and the signal can actually get attenuated and lost on a physical cable like that. Now we just simply, if you use a wired connection, how many of you use wired connections? Why do you use a wired connection? Because it doesn't suck like UBC Wi-Fi? Because if you actually want a game, maybe you want something that has bounded latency? I mean, anybody do first-person shooters or any kind of competitive gaming? It sucks on Wi-Fi. You know, it's great, and suddenly you get this big-ass lag spike and you're dead. And you're going, fuck. Well, there's at least a couple of gamers in here, obviously, I could tell, because people were smiling because they've had this happen. Right, so the reason that you use a wired connection is because it's much more reliable and stable. On an original Ethernet cable, what actually would happen is the physical hardware would look to see if there was a signal on the cable. And if there isn't a signal on the cable, it would then begin to transmit. And there is a period of time where the signal propagation can be it could be in an invisible range. So there's a collision period, is what they call it. If you notice that someone else is also using the cable at the same time, you stop using it. Now, if everybody stops using it for the same amount of time, what happens is we jump back on it again, we do this again. We jump back on it again, we do this again. How do we fix that problem? Now you know the problem, what's the solution?
Different times.
Yeah, right. We just need a little bit of randomness in this, right? We just need to do a random backoff is what actually happens in networks. And we do that a lot because that's the way that we break these kinds of storms. So there you go. What happened here was they didn't do that. So the clients were all sitting there literally timing out and retrying at the same time. Bam, 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 bam. And that then causes the intermediate nodes to crash and burn and so on and so forth. So what's the lesson here? When we build resilient systems, we have to think about the kinds of failures we're protecting against. And we have to learn from what we've learned in the past. I mean, that's kind of the way humans learn. We do it wrong. And then we do something else wrong. And then we do something else wrong. And usually I joke that my approach is I do everything wrong. And then when I run out of things to do wrong, I'm forced to do it right. So the question you should be asking yourself when you're thinking about when you're doing these designs is, what is the guarantee the network is providing to me? And there's no single answer to this because this is going to depend on what the network is. When you start designing data centers, how many of you want to be data center designers? How many of you want to work for Amazon or Microsoft or Google doing cloud stuff, web stuff, or AWS, Azure, Google Cloud Platform? Why do you want to work for them? Am I wrong? How many people know what kinds of salaries the folks at Google get? What do they make?
Like low to mid 6 figures.
There you go, low to mid 6 figures. And I can tell you that if you can actually explain Paxos, they will eat you up. And the reason is because it's a simple idea and it's a bitch to get right. Of course, right now, who knows? Maybe they're not hiring anybody. It's kind of hard to tell. There's still lots of people who are hiring. There are lots of jobs and lots of opportunities, and understanding the things we're talking about, understanding how to solve problems, understanding how to deal with failure is actually a really important skill there, because that's what makes the difference when you start talking about distributed systems, is learning not just, when you first start learning a program, all you're trying to do is get the common path, this simple little minimum viable platform version of it working. And you just simply ignore all the errors around that. And then as you get a little bit better, you start trying to deal with some of those errors. And then you get into these complex systems of asynchrony, and you go, I don't even know the order in which things are actually happening here. Because you no longer have linear ordering. Why would you ever build a system that doesn't have linear ordering?
Make your work a little faster.
A little?
A lot.
It can make it a tremendous amount faster. How many of you took 313? Anybody take Reto's class? What is it, 436A? Just operating systems classes, right? So in 313, you learned about something called a scheduler. The function of a scheduler is to simulate parallelism on machines that don't have that, and now everything has it. So we have multiple cores running multiple threads at the same time, and the order in which two threads runs is a Markov process. It's very, very weird. I mean, in theory, you can actually predict what's going to happen, but what you end up with isn't something that is deterministic. You end up with something that's probabilistic. Why? Because the hardware underneath you is probabilistic, because the very amount of time it takes for you to execute something is probabilistic. And so one time your code runs, everything works fine. The next time your code runs to exactly the same place, and it doesn't work right because the ordering of events was slightly different. When you talk about schedulers, what you're talking about is the fact that any time a thread is preemptible, it literally has to assume that a large chunk of time, well, this is a computer, so let's say a minute between any two instructions. If you start thinking about the world that way, you'll go, whoa, that really does mean I'm going to have to do things differently. Well, that doesn't happen very often at the single machine level, but now we put these machines talking to each other over a network, and suddenly that kind of variance becomes much more routine. This is what's going to make this all hard. And you have to think about that particular failure model, what the network is promising. The network didn't promise to deliver the packet to you within some bounded amount of time, and there are networks that do that. You can run real-time networks, and you can get bounded guarantees. But when you run over the internet, yeah, right, that's bounded guarantee. There's no time guarantee. You can limit how many hops it can go through, but you can't limit how long an individual switch held the packet. You can't control the fact that sometimes one of the packets in the middle gets lost, and therefore the packets arrive out of order. Retransmission just makes the problem worse. So what did we add retransmission for? Well, to handle the case where a packet gets lost. But now that means sometimes the packets could get lost 3 or 4 times. TCP is well known for being able to make forward progress in as high as 90% packet loss cases. But it's going to suck. You're not going to want to go out to a game on a connection with 90% packet loss because everything's going to take a long time. But it'll continue making forward progress. As long as you're making forward progress, we consider the system to be operating within normal parameters because, of course, the system is, let me just open that up, well, whatever, is alive. And aliveness is an important property of distributed systems. There's going to be these 3 things we focus on. Aliveness is one of them. Consistency is another one. Consistency is hard. And then the bane of our existence when we start talking about networks, which is partition. Anyone know what a network partition is and what it means? All right, well, we'll get there. There we go. Best effort packets can be lost, delay, duplicated, reorder, partitions. Oh, there we go. Gee, now we're going to learn. The network can actually fail without any node crashing. In other words, the network itself fails, not the computers using the network. If somebody unplugs a cable accidentally, or the cable gets broken, or a backhoe picks up a piece of fiber optic cable that it wasn't supposed to have picked up and breaks it, all those connections that were using that can no longer use that. But there are machines on either side of that that continue to work and continue to talk to each other. This is going to be one of the harder failure scenarios for us to deal with, because when we talk about distributed databases, the worst thing in the world for us is to have a partition of our database where each of the partitions is making mutating changes to the database itself, at which point you go, oh my gosh, how am I going to actually fix that one? I mean, there are approaches. You can handle partition. Yeah.
What exactly are partitions?
They're literally where the network is split into two or more pieces. So reachability, right? Because the network is a big graph. Imagine that you just simply went through and cut through some of the vertices of the graph. And then you no longer have any paths from one part of the graph to the other part of the graph. TCP actually makes this better for some sort of local delivery, where local delivery could actually be on your continent or it could be on your planet. But it doesn't solve the correctness in distributed systems because TCP can't make up for things like partitioning. If you can't get the packets through, it doesn't matter that you've got a protocol that would recover it when you restore it. One of the failure examples I used last time I taught this was actually a really cool one where this company called GitHub, maybe you've never heard of them. They had an optical transceiver in a switch that was experiencing a higher than average failure rate. And so what they said was we need to replace this. So it was a planned outage. It wasn't unplanned, it was planned. They planned the outage, they turned the device off, they switched the optical module, the failing one with the non-failing one. And the network was partitioned for 42 seconds. It took them, I think it was 2 weeks to prepare when they ended up with two divergent copies of the data they had across the data centers. And that's what partitions can do. 42 seconds. It can cost you a lot more than 42 seconds at a time. So the failure models. So you have fails out after the machine crashes, and it never comes back again. There's actually a failed recovery model where the machine crashes and resumes, and you can't tell it apart from fail slow. So it fails because the machine is slower. When the machine comes back, it starts to process packets again, and it covers. You can't tell the difference between that and the machine rebooted and somebody unplugged the network cable, so that is not getting through. Byzantine is actually harder in that it means that the communication is disrupted in some form. I use that in the Byzantine Empire sense where you're actively lying. So Byzantine could be malicious, or it could be broken hardware. I mean, there's no maliciousness there, there's no intent there. But you can actually distinguish the two. That's what's really interesting about it. You can't tell if somebody's trying to attack you, or if the failure is just a failure. And each of these problems, it's easy to describe them, and it turns out it's a nightmare to actually handle them. Have any of you ever heard of blockchain? How many of you have dabbled in cryptocurrencies? How many of you built web add-ins to mine cryptocurrency on other people's computers? Right. Of course I want to do that. I pay bills somehow, right? What is blockchain? Go for it.
One very different keeping track of very list microtransactions. It's a big distributed system.
Actually, the signing technique we're using for your repos is sort of like a blockchain, but it isn't really distributed and big. But it's the same basic idea, which is that you use something to compute a value, which you then use again, use the output value as an input to the next stage. And what you want to do is make sure that going back and changing those becomes computationally prohibitively expensive. Maybe something for Bitcoin. No? I mean, what do people use Bitcoin for? I mean, wholesale value, right? What do you buy this? Turns out actually, there's a whole business around trading like military-grade weapons using Bitcoin. Is that because Bitcoin is impossible to trace? Is Bitcoin impossible to trace? He says no. He might say yes. There's only a debate here. It's difficult, but it's not impossible. In fact, the weak spot in Bitcoin trading, the way that we end up tracking people down is because they want to turn it into something that they can spend in the real world. So if all you're doing is actually doing Bitcoin exchange, it's a lot harder to figure out. But when you try to turn it into a different currency, then you have to do it with an agency that's typically registered, and that's the weak spot, because that's where you have to show somebody's identification and map your identity to the Bitcoin wallet that's being used. Well, the purpose behind that is to point out the reason we have blockchain is precisely because it's also a Byzantine problem. We have a whole bunch of different computers that we don't trust. How do we get them to agree on something in a way that, even though we know that some of them are lying, we can in fact achieve consensus? And we'll talk about that because that's a very interesting result. So partition versus crashes, you can't really tell the difference. That's one of the complications of them. It's a message over to you, you don't answer. I don't know if it's because you're dead or because the carrier pigeon I used to send you the message died. Or maybe just was hungry and stopped to have lunch. I don't know, I can't tell. If you're ever in a very bored mood, you can look at them. I think it's RC1049, which is IP over carrier. In other words, they used carrier pigeons that put messages and send them. And then someone else thought that was a great idea. They built the quality of service on top of it. This is what you're doing when you're another person in your board. Go first. Okay. Your critical only relativity is a failure model. In other words, if you experience failures in a non-failure model, then you're not likely to be able to survive it. You might get lucky, but probably not. And so the lesson here is, like I said before, everything that you can think of that will go wrong will. It will handle it. And things you never even imagine going wrong will also go wrong. And then you'll have to go back and modify your model of failure and protocol you use to recover from those failures. And that's the way it works. Timeouts are not actually detectors. It's actually really using a whole host of a serious work where people can use timeouts as detection of failure. It doesn't unfortunately work because of partition. But even though it's not the perfect solution, we often end up using it because a reasonable proxy in many cases where what we can say is, well, you know what, if the packet is more than X old, X days, X years, X months, whatever, old, I'm just going to ignore it, I'm just going to drop it. Can you see what problem that is? Yeah, okay. There's another problem. There's actually more fundamental than that. There's something we're assuming implicit in that description. What? Yeah, that happens. But what are we assuming here? There's an interesting assumption in that model that nobody's picking up on yet. There's this guy who in 1908, in the early 20th century, there's this crazy guy, you've never heard of him, Einstein, who constructed this crazy ass idea that in fact the flow of time depends upon the perspective of the observer. It's called special relativity. Special relativity actually says we don't have a universal clock. You say, well, that's fine, it's close enough here on Earth. Sort of. In fact, there are even spots on the surface of the Earth where time travels at different rates with other spots, believe it or not. But the easiest way to see this is when you start talking to satellites. They got to have satellites up in the air around us, right? It's not like they're interfering with telescopes or each other now. Of course, talking about right now, where they're literally describing is the guys saying that we actually predicted, especially we end up with a situation where there's so many satellites and bad satellites around the planet that we would be able to actually travel through it, and we're getting there. Starting to move satellites because they were bumping up against other people's satellites very recently, within the last couple of weeks. And so the solution was moving below orbit, so what we're doing is just kind of like continuing dumping into the atmosphere. But when you put things in space, there's a relativistic effect, and clocks actually don't run as fast. The GPS satellites, which have been up for a really long time, the GPS satellites actually have to correct for relativistic behaviors. So that's fine, as long as the relativistic effect is small compared to the time sensitivity we have, we can probably ignore it. But the moment we can't ignore it anymore, then we have to start thinking about it. What do we do when everybody has a clock? They have the same clock. Timeouts mean crash partition congestion is slow fail, where you can't tell if it's machines are doing or if apps are being discarded. Garbage collectors. And people write system software don't use garbage collectors for a reason. They create kind of difficult to deal with just puzzles. I mean, application programmers use garbage collectors all the time because it's easier to think about. You know, it's like filling up your apartment with full pizza boxes until finally you don't have any place to walk and you say, okay, now you have to clean up. And then you spend 2 hours taking these boxes down to the recycling bin. Not many people do that. Retries are also failure amplifiers I talked about before, and when we are building correctness, we have to understand what it is we're trying to keep. I know this is important because it was the example I used earlier when I asked you what time it is, and back in the last 3 times, I want to know what the time was when we got the first one. I want to know what the time is on the last one. Question.
About the relative time thing. So say that we have two competitors and time passes differently in one and time goes over the other. Would we not just, if we know that that's the case, and just let that adjust from one in one place and actually the other out
So you're assuming that the rate at which they're different is constant. No, it's not. Anybody know enough physics to explain why? If you could keep the acceleration between them constant, then you could actually blow the trick off. The problem is that almost nothing maintains the acceleration being constant. And even when we look at our solar system, we end up having to deal with relativistic effects on dealing with the moon, dealing with the planets that we're talking to the Mars rovers. And they're accelerating away from us towards us at different rates consistently. It's never a continuous amount. Now, in that particular instance, it's probably possible to come to the model is close, and we can do some manual adjusting, but there's this problem in physics known as the 3-body problem, which itself is just another instance of the 3-body problem, and actually pretty good approximations of the 3-body problem. Away from the 3-body problem, we need a 30-body problem. And yeah, there's solutions to that. But we will deal with all this. There's this crazy dude that came up with an interesting model for how we can accomplish this, and we'll talk about that. It's called the vector clock. Practice requires dealing with things like ordering, duplication, back, potency. These are all different things that people mentioned already this morning. So what do we do? Here's a nice little cheat sheet of things to think about. Use sequence numbers. Sequence numbers are like a clock. They provide an order. See, this is the interesting thing. The clock, it turns out, isn't important to be the same. It merely needs to be enough that we can reason about the order in which something happened relative to someone. If I send string packets, and I keep increasing the number, then I know what, when it multiplies by I know what the correct order is because I know how to order the packets relative to the sequence number that was used with the clock, that was used by the sender. That's fine as long as it's just two-way. When we go anyway, it becomes more complicated. But we can, in fact, do something called vector clock, which is, what's the last sequence number I saw from you, the last sequence number I saw from you, the last sequence number I saw from you, and from you, and from you. I've never seen anything use on how the entry in a vector yet. How do you message from you? The vector goes, and the vector clock goes. Anybody ever last? It's a mathematical structure. It's actually really important because vector clocks tie in well with lattice theory. And we're going to use them in distributed systems because we're going to focus on something called visual consistency, which we can do with lattices. We'll get there. Duplicating hashes are interesting. If you actually, so I got the DSLab stuff all deployed this morning, and you can actually see that it implements what's called exactly one semantics. And the way it does that is a client, it's like a process, it could be a thread process, it could be a single continuous communication channel. A client never advances to the next request until it's an answer. I mean, command in that communication channel, but it doesn't ever proceed to a higher number, a higher sequence number when it's sending packets. So it can be transmitted infinitely. And on the other side, the server guarantees to only request a request at most once. So at least once from the client, at most once from the server, and the intersection of those is exactly once. And that's what everyone uses. I'm going to use a different concept, and that is that the operation is in fact standalone. And there are ways we can do this even when they provide out order. There's things called CRDTs and RDTs, which are both interesting because what they are is composable operations. As long as the order composition doesn't matter, the order in which we process the request doesn't matter. This is what we lead into a very nebulous system where eventually, in the fullness of time, we'll end up with consistent views of the world. We use explicit acknowledgements, that's not fun. We use timeouts and backoff, so like the retry farms use non-terminating backoffs, so that we don't all keep pounding at the system at the same time. And finally, we build in observability, so that we can see what's going on inside the system. So I usually walk through this because I spent a bunch of time recently looking at LLMs. And you know what? It actually exactly what it's running here. So right now LLMs don't have observability. It's sort of good, but it's not a standard feature. All we get are just messages. We don't get vector clocks. We don't get the information about what's going on inside. I'm going to skip this for a moment. I do want to do this one, something important, I think. So if you go to your GitHub repo, everybody should have a repo, you should see it. It should be whatever your name is. Probably CWLs, I think it is. Yeah, right. And it was like, I can make it more specific than that because every CWL is unique by definition. So you should be able to see your CWL in class GitHub. Is there anyone who can see? This is the problem. I can actually confirm this because I can see everything. And so I saw one person raise their hand, so that means it will work for everyone, right? You're like, yeah, right, if you were to do the class since I ran the script that does that, you won't have one yet, and I will run the script again. Although it had a lot more people that are actually in class, so I think that in fact the CSIT folks put everyone on the waitlist as well as everyone who's in class. Things like it repo, or like how it works. Should be able to clone it, do it machine. Using your SSH key, because everyone has SSH key. Using your SSH key is easier to sign it, but if you want to do it like you would do for, I don't know if you're working on something that's probably using GPG. GPG stuff is a little more complicated than SSH, but everybody needs to be smart. So you have the where I did. And it's very fussy. The UBC student GitHub requires you to use the exact email address that it thinks you have, which appears to be students. CWL@students.csm.ca. If you don't use that, sign it, GPG, sign it. If you install the hooks, it will actually automatically validate locally. If you don't install hooks, they will actually be enforcing push to GitHub itself. GitHub Enterprise Server. That's github.students.csm.ca. It's actually cool because once you do this, you start working on the open source project, you'll be able to easily sign your commits to them as well. And have a nice little badge next to verify. Makes you feel like you're almost responsible. Yep. Never mind, figured it out. I love those questions. That's the bugging. Where you start trying to explain the problem and add explaining the problem in real life and understand how to solve it. If you look at the GitHub, go to your profile, it will tell you what email it's using. But at least starting to tell it's users. CWL with a, yeah, that's okay. Actually, we're taking this approach because there's no problem with academic conferences where they get what they're called nice thought papers, where people use, Gemini, ChatGPT, or Kimi or Claude to rapidly forget there's some piece of bullshit paper and submit it. And the reason this works is because anyone who actually writes papers ends up working on them over time. So you have a revision history. And if you have a revision history, well, it doesn't prove that you're sitting against law. It means that if you're writing a program committee, you at least know what to look for. You look at people who don't have that kind of thorough history. So that's a little suspicious. Eventually, I suspect what happens because of that problem. Those require it. There's supposed to be information kind of strategies as well. But I just want to things to go fast. What? Kind of wet. I can't hear you. I'm old and deaf. No, as well, right? Yeah. Because what Script is actually really good site. Git config user.emails email git config. Yes, but it's yeah, I'll do my. How do this actually my file? This is my file in my Git directory. Fix it. my get config looks like. And the keys here are, you set commit, set GPT signed to true, you set user email address, you set sign D2, I'm using GG. I didn't have this installed, but as I said, it's supposed to be simpler. And so the idea is what that'll do now, and because the config file is not part of the repo itself, if you move different machines, you have to actually move the, you can reset that config again. But the point is, once you do this, it will actually prompt you every single time trying to get something. So let me see if I can demonstrate that. 41 CPSC 416. I'm going to give you a file. That's not a file. And you'll see it pops up. And then when I push it works. It doesn't work. Well, normally it would reject it from the idea of, actually that's fine. You can fix that. It's not a complicated step. So let's get working and then just stick with it. When you have pretty low overhead. There's an initial friction and stuff. That's the other. There's one more thing I have to do. Yeah. You can call it what you want, right? So obviously, when you pull that template, in order to structure it, there's going to be stuff for it. So, and then the idea is that we're going to use that structure in order to figure out use evaluations and whatnot. The idea is that FDH will need to also wrap the term and find feedback. So I decided to try to the locus of everything you do. So you have one place where you're putting things in class, things that you do as submissions projects, and so on and so forth. And when you get doing group projects, if you do group projects, then what you do is have a file that says, this is the repo of my group. And this is hashed outside file. The idea is that by doing that, it protects you because you will sign that and part of your repo will know that you done that. And it means that you're intimating something here. We're going to fuck them. We're just going to turn this trash. You can find the payment, they change after I signed off. So it's an attestation. I mean, not that any work with a group ever doing anything like sabotage, right? Has anybody had a group member try to sabotage him? Accidentally deliberately? It's a good example of behavior. I don't just buy it. Honestly, I totally get that. I mean, I wouldn't bring messages right now. No, I'm not being right now. I'll do it instead. Because I won't be able to back. Alright, so you can finish up. I know we get started. You can ask questions, we'll figure it out. I just lots of links. One of the things that doing that is using AI, you have to. If you really don't want to just say I chose not to use it at all, but of course, you know, there's no penalty. I'm kind of looking at going, yeah, are you sure? Yeah, I'll like dashes and all that actually didn't use AI generate. And you can see I always use dashes, my favorite punctuation character. The problem is there actually is no way to tell if it's generated by an AI versus generated by you. But people convince themselves they can tell the difference. So you know when somebody's lying to you, right? Until they're really good and they lie to you, and next thing you know, you find out that they have your bad account. So there's a lot of stuff. So you can use actuals and they effectively log it, just put it in there. And that's usually when you actually sign. In the ledger, you can add it in there, and in you can put reading there if you want. So don't forget that you have readings, more readings in the quiz. I put everything that's two quizzes I put into the module as well, so you can see the module quizzes from the quizzes. I don't really care. If you want to go in there and basically like bullshit for it and click submit, fine, you get credit for it. I mainly get credit, it doesn't automatically do that, but all I'll do is submit it to the everybody else one, and don't get credit for it. The self-assessment's always open at 1 p.m. and then closed at 11:30 a.m. before the next class. So the idea is to keep you doing that, spending not before 2 minutes. All of the quizzes help you evaluate whether or not you gain some understanding of the readings. If you're reading the readings, it's probably very helpful for you. I know it's a lot of reading, but again, I'm expecting to be doing skim, not the deep dive. If you feel like you're deep dive, go for it. That's not an expectation. These tabs is everything is now unlocked. So you have to see them in the repo. They are named. I actually started them on mine, so I can find them. Probably you'll see like 5 or 6 saying what your own was. So these are published. They allow you to start playing with the framework itself. And so the framework in this case, we're not using those written design, which was actually using a bit of code and then leaderboards and shit and try to make sure their implementations really fast. I'm about that. I'm using it as deterrence. So what you're going to do is you're going to use the backup, under backup, replication server and the access server implementation in the design projects. And that's going to be weak when you get someone else's design. I don't think they do a good job because a lot of you guys know and you should know about that. The object isn't actually the code works. You don't believe code works. Somebody's design, you should basically be saying this is what the design looks like. If you have something design and they set a thread at the top because you want to get credit for saying something, you pretty much off the hook. So you simply say, well, you know, I'm submitted it, and we're trying it. So the goal here isn't to make this class nightmare for you. The goal here is to get you to do things. When you do get to capstone, you're going to actually make a difference. And you should probably start talking about this. Please talk about when you capstone. I have I'm going to pull a series of designs from the parts. I'm just going to make sure there's naming things. I just want to today. And I'll show you see the range of possible options. As long as you come up with an angle that can stop this, this is enough. So let's see what else. Anything else? Let's keep it. So yeah, I will see you next Tuesday. Have a good weekend. Hopefully, you're not going next week. We're going to everything's going to be bullshit. And it's like, that was 0. You guys just put it on Twitch. Alright. Everybody, anytime you stream doesn't work very well, you see anymore. So I think what I need to do to make it work right is I need to VPN someplace so that UEC doesn't know that I'm streaming Twitch. Yeah, I know that. Oh my god. I mean, you hear that? Because the first one that actually streamed worked pretty well. Some people do it a lot. And you're right. I mean, I'm going to extend stream mode and start doing that. Hey, how are you? I'm alright. Let me stop the recording because otherwise, some stream will I'm pretty sure it. Okay, guys.
The question about the Senator 460.
This is for 60.
But this is for the 3 class.
It's easier classes. 3060.
I see. Okay.
436.